Okay, I wanted to review some of the material we already covered in class because it's been a while since we looked at it, but I'm going to go through this first material pretty quickly. This first slide is showing the overall structure of the Earth. Now, labeled up here is the magnetosphere, and that's referring to the Earth's magnetic field, which extends well beyond the Earth's surface. And then you can see this sort of blue haze, this thin film that's clinging around the surface of the Earth. That's the atmosphere. And that really gives a sense of perspective of just how closely to the surface of the Earth the atmosphere is. It doesn't extend that far into space, as many people think. Then there's a very thin crust, and then underneath the crust is the mantle. And then finally going all the way down to the center of the Earth, you find the core. And the core is broken into two parts. There's an inner core, which is solid, and then there's an outer core, which is liquid. Now we'll talk about how we know that there is that region where it's liquid later on. But the fact that it has got a liquid part and a solid part is going to be very important. Now the atmosphere, which clings around the surface of the Earth, is made up of a series of gases, primarily nitrogen and oxygen, but also some trace amounts of things like carbon dioxide as well. And then you have the hydrosphere, which is basically the Earth's oceans. It's the water part that is mainly on the surface of the Earth. Okay, we've already been through how to interpret this graph previously, but I wanted to go through it again really quickly. The main thing that we want to look at is this blue curve. Now we have three different axes to consider. There's the left vertical axis, which represents the amplitude above the surface of the Earth, measured in kilometers. There's the horizontal axis, which is temperature, measured in Kelvin. And then there's the right vertical axis, which measures the pressure of the atmosphere relative to the ground level. In order to interpret this graph, we have to consider this blue curve. That's the relevant part of the curve. And so we can pick a height. For example, let's pick 100 kilometers right here. I can go straight over to where that 100 kilometers intersects the blue curve. And if I keep going to the right, I'll come over here, and on this right vertical axis right there, I can see that it's about 10 to the minus 6 and a little bit less than 10 to the minus 6. If I continue, if I go straight across from that 100 and then go straight down, that tells me the temperature. Now, that looks to me, here's 150, here's 200. In between them would be about 175. So again, if I go from the 100 straight over and then come straight down, that's a little bit more than 175, maybe 180, 185. And so that would tell me that at a height of 100 kilometers above the surface of the Earth, the temperature in the atmosphere is about 180 Kelvin. That's about minus 140 degrees Fahrenheit, just to give you some perspective. Now this graph also shows different parts of the atmosphere. The atmosphere is bound up in different layers. The layer that's closest to the surface of the Earth is called the troposphere. The layer above that's called the stratosphere. Then there's the mesosphere and the ionosphere. Now what's interesting is that the troposphere, the region that basically is where the cloud level is and below, that's the region of the atmosphere where weather takes place. The stratosphere, which is the next level up, that's where the ozone layer is contained. And the ozone layer, as we talked about, provides protection from the harmful ultraviolet rays of the sun. Okay, in this slide, we're looking at the process of convection. Now, convection occurs when the sunlight comes down and it warms up the ground, and that warms up the air close to the ground. As the air gets warm, it expands and it becomes less dense and it rises. The cooler air up above is heavier, it's more dense, and so as the warm air expands, the denser, cooler air falls down. But then now the cool air is on near the ground and it warms up, and this process repeats over and over. So it creates cycles or currents of air in the atmosphere. This process of convection is the primary driver of weather because that's constantly creating motion of the atmosphere. This slide is talking about the ionosphere, which is the outermost layer of the Earth's atmosphere. It's called the ionosphere because it's literally ionized by solar radiation. That means the energy of the solar radiation causes electrons to be ripped off the molecules. That leaves the molecules positively charged, and they're just kind of a soup up there of positively charged molecules and free electrons that have been ripped free. And an interesting quirk of this is that this region reflects radio waves that are in the AM range of the electromagnetic spectrum, where AM broadcasts are sent out. But it's also transparent to FM and TV broadcast frequencies. That part of the spectrum the atmosphere is transparent to. So we talked about how there is an optical window to radio waves. Those regions, the FM and TV transmission bands, those are big parts of the electromagnetic spectrum where the atmosphere is transparent. And of course, we already talked a little bit about the ozone layer, which is a region of the atmosphere that absorbs the most harmful parts of the ultraviolet radiation in the sun's spectrum. This is, of course, important because ultraviolet radiation is higher energy than visible radiation, and that makes it dangerous. And if you have UV light incident on your skin, it can actually cause damage at the cellular level and create cancer of the skin. Now, there are chemicals called chlorofluorocarbons, and that's a mouthful. Usually we just refer to them as CFCs. These chemicals were used very widely during the 20th century in refrigerated systems. But as they leaked into the atmosphere, it was discovered that these chemicals actually break down the protective ozone layer. And so they have since been banned. This became a problem when it was discovered that in the southern hemisphere, above the continent of Antarctica, there was a huge hole in the ozone layer, and it was expanding. And they traced it to the presence of these CFCs, and that's what caused them to be banned. Now, CFCs are an example of something called a greenhouse gas, which we're going to talk about shortly, but they're in very low concentrations in our atmosphere now, so they don't actually contribute that much to the greenhouse effect. So what is the greenhouse effect? This is an effect which is responsible for much of the heating of the surface of the Earth. Now, sunlight comes in, it goes through the atmosphere. Some of the sunlight is reflected back into space. It's reflected by ice caps on the surface of the Earth, it's reflected by clouds in the atmosphere and other things, but much of it is not reflected. And the part of the sunlight that actually makes it through to the surface of the Earth gets absorbed by the Earth's surface, and that causes the Earth's surface to warm up or heat up. Now, as we know, anything that has temperature radiates energy. So as the Earth's surface heats up, it re-radiates that energy back into space, but not as visible light like the sun, because the Earth is at a much lower temperature than the sun. It radiates as infrared thermal radiation, or radiation in the infrared part of the spectrum. The atmosphere then absorbs that infrared radiation, or at least a large portion of it, and that causes even more heating of the Earth. This effect is called the greenhouse effect because it acts like an actual greenhouse, where a greenhouse is a glass building that usually contains plants. The idea is this: the sunlight comes in, and of course sunlight can pass through glass, and so it passes through the walls and the ceiling of the greenhouse, and it lands on the plants and it warms them up. Now these plants re-radiate thermal radiation or infrared radiation back into space. Or it would go back into space, except it encounters the glass. And the glass actually blocks infrared. So it lets the visible light in, but it keeps the infrared light trapped. And thus the greenhouse gets warmed up because that radiation cannot escape back into space. In our atmosphere, there are some chemicals, mainly carbon dioxide, that works like the glass of a greenhouse. It traps the infrared radiation, but it lets the visible light pass through. So the sunlight can come through the atmosphere, warm up the Earth radiates infrared, but that infrared radiation is trapped by the greenhouse gases in the atmosphere. And this effect is known as the greenhouse effect. Here we can see this represented in a picture. You have the visible sunlight coming in, some of it's reflected back into space by clouds, but some of the sunlight gets to the surface of the Earth, it causes the Earth to heat up, the Earth re-radiates that energy back into space as electromagnetic spectrum in the infrared part of the spectrum, but that infrared light gets trapped by the carbon dioxide in the atmosphere. Carbon dioxide is one of those chemicals that acts like the glass of a greenhouse, and it traps the infrared radiation and heats up the Earth. Now, over the past century or so, we have been digging up carbon in the form of fossil fuels and burning it, causing carbon dioxide to be released into the atmosphere. And we've put so much carbon dioxide into the atmosphere that the Earth is actually warming. And it's causing lots of problems, and it will cause a lot more problems in the future. But that at least gives you a basic understanding of how the greenhouse effect works.